Hey there, folks, back here with almost to the end of our videos here, very close to the last video in this series for Calculus 1. There is a few topics I might add here after this video where I think we might want to spend a little bit of time still this semester. However, I think this is pretty darn close to the end and pretty darn close. Well, this is probably going to be a wrap on terms of technique and calculation technique for integration this semester, folks. So, what we're going to look at in this set of notes is an advanced integration technique. I've kind of mentioned this before. We have, when it comes to finding antiderivatives and calculating definite integrals, there is at the moment basically a set of 14 fundamental rules. 3 that are basic, that are power rule, constant multiple rule, and sum and difference rule. And then we have 11 other specific antiderivative rules. Like, for instance, the integral for the cosine of x is the sine of x, or the antiderivative of sine of x is the opposite of the cosine of x, and so forth. All right. Well, to add to that list of fundamental rules, we have an advanced technique that makes use of some of those rules. Well, it makes use of all those rules, as well as at times also is going to incorporate a little, well, it is going to incorporate a little bit of differentiation in the calculation. The rules for derivatives, right? And an understanding of chain rule and chain rule for derivatives. All right. I open up with this example here, and I think I may have shown you this in class already, or this has appeared in the notes, where we just consider the antiderivative for the cosine of 2x. And we know from that list of rules that the antiderivative for the cosine of x is simply sine x. And from a little bit of knowledge about that antiderivative and what we know about differentiation, we could probably determine with just a little bit of hard thought, thinking a little bit about this, that the antiderivative for the cosine of 2x could be written as 1/2 sine of 2x plus c. Right? Where the antiderivative function 1/2 sine of 2x is our antiderivative because its derivative with respect to x would yield the cosine of 2x from some chain rule. Right? Maybe I should say that. Yes. From chain rule, this derivative is equal to 1/2 to sine 2x, right? Oh, cosine 2x, where times that 1/2 is what simplifies to the cosine of 2x, right? In our end value, and that all develops from chain rule, right? However, if we didn't want to think too hard about it in terms of calculation, there is also a technique we could use known as variable substitution. Here in variable substitution, to work through this process, we would consider letting u replace the value of 2x in this calculation. If u equals 2x, that argument, the cosine of 2x, can actually be written as the cosine of u. And the statement du dx, right, the derivative of u with respect to x, the derivative of this statement here that we initially declared for the value of u, its derivative would be equal to simply 2. Where with a little bit of algebra rewriting, right, dividing both sides of this equation by 2, and multiplying both sides by the differential dx, we could rearrange this statement into saying that 1/2 du must be equal to dx. And with that acknowledgement, we can go back into this definite integral calculation, or this indefinite integral calculation for the antiderivative of the cosine of 2x. And we can substitute in for the value at 2x the variable u, which will make that into the cosine of u. And likewise, we can replace the dx with the statement 1/2 du. Replacing this with dx with 1/2 du, we can build this argument given by the antiderivative for the cosine of u times 1/2 du. Where I can do a little rearranging to begin with, right? That 1/2 is a constant multiple, and it could actually be brought all the way out in front as a constant multiple of my antiderivative, where here you can see I'm interested in just the antiderivative for the cosine of u du. Which in terms of x, we know is the sine of x, whereas in terms of u, this would be equivalent to the sine of u. So we would be able to write this actually as 1/2 sine of u plus c. Now that is not our end result though, because our initial definite integral was all in terms of x, not variable u. But what we do understand is that u is equal to 2x. So since u is equal to 2x, we can end up concluding that the antiderivative for the cosine of 2x dx must be equal to 1/2 sine of 2x plus c, substituting in for this value of u inside of 1/2 sine of u, the value of u equal to 2x. Right? And we can find this result of 1/2 sine of 2x without having to think too hard in terms of what would produce, well, what function's derivative would produce the cosine of 2x, whereas I could just perform a little variable substitution by letting u equal 2x in this argument and manipulating the derivative of that value of u to substitute in for the value of dx. This is called variable substitution. If we were to look at another example illustrating variable substitution, we might consider the antiderivative for x times the square root of x squared plus 1, all integrated with respect to x. Now this one we aren't going to simply, I think, with hard thought necessarily stumble upon what is going to be the antiderivative of this function. And when we see the end answer, we'll probably say, yeah, I probably was not going to think of that answer as the antiderivative. So having some technique to calculate this antiderivative would certainly be useful. And what we can use is a little variable substitution. Now in variable substitution, how it usually initiates itself is you want to look into your integrand, the argument of your integral here, and you want to look for a composition. That's really what you're going to highlight as a composition. And if you look at the square root of x squared plus 1, that is a composition between the square root function and the function given by the quadratic x squared plus 1. We're taking that quadratic and substituting it into the square root function. And we're forming a composition with those two functions. And that is being multiplied out in front by this other factor of x, where that x is necessary to finish this integral. What you'll notice is that x is actually a multiple for the derivative of this interior function x squared plus 1. And that's going to be important in this calculation. Where I have this composition, I want to declare u to be the interior function in that composition. Just as I had done previous with the case for u representing the 2x inside this composite with cosine of 2x. Here I'm going to let u equal x squared plus 1. If I let u equal the quantity x squared plus 1, its derivative will yield the value of 2x. The derivative of u with respect to x would be 2x. And with a little manipulation, I can rewrite that quantity as 1/2 du equal to the statement x dx, where this x was necessary to pair up with this value of dx to be able to substitute out with the value of 1/2 du. And all of that developing from the derivative of my value u with respect to x. Substituting in for the x squared plus 1, the value of u, and substituting in for the value of x dx, the value 1/2 du, I can form the following argument. Now you can see here, took my antiderivative, and I took that factor of x and paired it back here with the x dx. And what's going to happen is it's going to be replaced with 1/2 du, and the argument under the radical is going to get replaced with the square root of u. This will become the square root of u, and this will become 1/2 du. We'll have, in a sense, the antiderivative for the square root of u times 1/2 du. And that x was necessary to pair up with the dx. And you'll notice that x is a multiple of this derivative of u with respect to x. It's half of it. Right? It's half of it. So substituting in 1/2 du for the x dx, I can move that 1/2 to the front as a constant multiple. And how we handle the antiderivative of the square root of u, we're going to use a fractional power. That's going to be u raised to the power of 1/2. We're using a little power rule. That's going to bump up to the 3/2 power. And dividing by 3/2, we're going to yield the value 2/3 u to the 3/2 power. So I end up with this result, 1/2 times the antiderivative of u to the 1/2, which is 2/3 u to the 3/2 power. Increase the power of 1/2 by 1, adding 2/2 to it, it'll become 3/2. Dividing by 3/2 is going to be like multiplying by 2/3. It's reciprocal. So this will become 1/2 times 2/3 u to the 3/2 plus some arbitrary constant c to make a family of solutions. Now, we can't leave that as our final answer, though. We want a final answer in terms of u, and you can see I cleaned this up a little bit. The 1/2 cancels with this 2 in the numerator to leave 1/3. But we don't want to leave this just as 1/3 u to the 3/2 plus c. We want a final answer in terms of x. Now, u to the 3/2, notice that does simplify into the statement u square root of u. But because u is equal to x squared plus 1, we can come back in and substitute in for those two values of u and the u under the radical here, the value of x squared plus 1, and my antiderivative for the value of x times the square root of x squared plus 1 is going to be the quantity 1/3 times the quantity x squared plus 1 times the square root of x squared plus 1 all plus the constant c in value. And as I had hinted to, we probably weren't going to think of that on our own. All right? And what, again, this illustrates is a technique known as variable substitution. We're going to substitute in for the variable u for this quantity x squared plus 1. And this is all a technique that develops from chain rule. In general, I'll say here, from chain rule for differentiation, right? Let's say we know the derivative with respect to x for the composite of f with g at x is g prime of x times f prime evaluated at g of x. It is the interior function's derivative times the exterior function's derivative reevaluated at our interior g of x. Right? Which means if I apply the antiderivative operator to both sides, that integral of dx to the left and to the right-hand side, when applied to the left, it's going to undo this differentiation. And it's going to leave the antiderivative of this result from chain rule on the right. And we'd be able to say something like this right-hand side, this antiderivative of g prime of x times f prime at g of x, all integrated with respect to x, would just be equal to the argument of our derivative, f composed with g at x, all added to the value of c. This is the result we have for variable substitution that comes about from applying the antiderivative operator to our result from chain rule. And this is the result we used above in our calculation. We actually saw it in the format seen here. Instead of using f prime in our calculation, we used little f, where little f's antiderivative we called out as being big F because big F's first derivative would be equal to little f. Cap f would be, its first derivative would be equal to little f, meaning that cap f would be the antiderivative of little f. And this is how we see the chain rule actually, or the method of variable substitution actually presented to us. And it is presented in the following theorem here. Basically, it says assume that you have the setup for a composite of two functions, right? Assume u equals g of x, implying du is equal to g prime of x dx, where g is differentiable on an interval, right? And let f be continuous on the corresponding range of g, right? And on that interval, then, the antiderivative of g prime of x times f evaluated at g of x, where here we have the composite that we're going to look for, where the interior function's derivative is presented here as as another factor in our integrand. And truth be, it is actually going to be a constant multiple of that factor. We've seen that back in the previous examples. With that substitution, I can substitute out this value of g of x with the value of u, and I can say my integrand turns into f at u, and the value of g prime of x dx, right, at g prime of x, that factor times this differential with respect to x, will just be equal to du. And I can substitute in the value of du for that. And what we end up with is this statement here, which is the antiderivative of f at u plus c, which I probably should take a step further and note is going to be the antiderivative of f at g, all added to the arbitrary constant value of c, where g replaces the u in our final calculation. And this describes the process that we performed above in this example here, letting u equal x squared plus 1. That implied that 1/2 du was equal to x dx, and we were able to substitute out for that x dx the value of 1/2 du, and the value underneath the radical became just the value of u. All right. And then in the end, when I obtained my antiderivative in terms of u, I did want to go back in and substitute in for the value of u its value in terms of x to obtain my final answer in terms of x. Right? Which is all being highlighted here in this theorem. Technical difficulties. Sorry, folks. Taking a little break there after about 20 minutes and trying to come back, and it had blank screen set on there. But I'm back. Quick break on your end. That is for certain. It just seems like a pause. But let's, again, this is the theorem that gives us the process of variable substitution. And the first thing I do show you with it is it can be used to develop some generic rules for integrations involving composites with linear functions. Right. One of the things we can do in general with this form is consider the antiderivative for a function composed with the linear function mx plus b. Right? I might say here, consider the linear function y equals mx plus b. Right? And maybe we'll say the library function y equal to f at x, right? The antiderivative of that library function evaluated at this linear function can be approached using variable substitution. You can let u be the linear function mx plus b, that is the interior function in this composition. And that will end up implying that du will equal just the constant value of m, the slope of that linear function. And with a little bit of algebraic manipulation, we can show that the value of dx can be expressed as 1 over m du. And substituting into the antiderivative of f at the linear function mx plus b, all integrated with respect to x, we can end up with the statement, the antiderivative for f at little u times the quantity 1 over m times the differential of u. Replacing the dx with 1 over m du and replacing the u inside of f, or the mx plus b inside of f, with the value of u. That 1 over m will bring itself out in front as a constant multiple. Right? And we face the antiderivative of then just the function little f with respect to u, which we know is going to be cap f with respect to u. And with that 1 over m in front, it's going to be the 1 over m times cap f with respect to u. And since u is equal to the linear function mx plus b, we can conclude that the antiderivative for a library function composed with a linear function is just 1 over m times the antiderivative of the library function evaluated at the linear function, plus our constant value of c. All right. And we can see that in an example here. All right. I say, consider the secant squared for the linear function mx plus b. What the rule above said, well, if we notice, for the function little f of x equal to the secant squared of x, the antiderivative is going to be the tangent of x. And that implies that if we look at the antiderivative for the secant squared of that linear function, it will be equal to 1 over m times the tangent of our linear function mx plus b. Since f, right, cap f, is going to be the tangent of x for our function little f, which is the secant squared function in our library, right? Or considered to be like our library function. We can put that into action in example. Here's an example. We might say find the antiderivative of secant squared for 1 minus 4x dx. And if I let u equal that argument 1 minus 4x, the interior function in the composition, our derivative with respect to x would be then negative 4 for that value of u, which means negative 1/4 du would be equal to dx. And we'd end up seeing a result very similar to what we found above. All right? Substituting into our antiderivative, negative 1/4 du for the value of dx, and u for the value of 1 minus 4x, we can say the antiderivative is negative 1/4 tangent of u plus c. This negative 1/4 being the value of 1 over m being equal to negative 4 in value. And thus, since u equals 1 minus 4x, we can say that that antiderivative for the secant squared of 1 minus 4x is 1 over the slope of that linear function, which would be negative 4, tangent of that linear function, 1 minus 4x. All right. Now, in terms of definite integrals, variable substitution is approached as I illustrate here in this theorem. Very similar setup to the theorem, except now we incorporate the bounds from a to b in our calculation. Where when we perform the substitution in the second step, letting u be that function g of x and du replace the g prime of x dx, we are also going to substitute in place of a and b what are going to be the dependent values of function g at a and at b. What we often think of as these values of x, a and b are values of x that we want to convert when we perform the substitution into values of u. And how we obtain those values of u is we use that function that we declare to be u in terms of x, that function u equal to g of x. So we evaluate now across the bounds from g at a up to g at b the value of f of u du. All right. Where we are going to take the antiderivative cap f at u and now evaluate it across the bounds at g at a and g at b, which is like finding cap f at g, little g at b, and taking away from it the value of cap f at little g at a. All right? Where here, adjusting our bounds works, those boundaries work themselves back into the calculation, right? As the values of u in the evaluation of cap f at u across those bounds. It's a little bit more going on here, but not as tricky, folks, I will promise you. This does get a little easier when you substitute out for the boundaries, you'll see, in performing a definite integral. Here's this example. Let's find the definite integral from 1 to 3 for x times e to the x squared. Now, e to the x squared, you'll notice, is a composite of the exponential function e to the x with the square function x squared. And if I let u, that function of g of x, be the function x squared, that is going to imply, I missed it here, du dx is going to be equal to 2x, or 1/2 du is going to replace the value of x dx. this x dx will get replaced with 1/2 du, and the x squared and e to the x squared will get replaced with u. Also, when x equals 1, we might point out u is going to equal g at 1, which is 1 squared also equal to 1. And when x equals 3, u is going to equal g at 3, which is 3 squared, which will equal 9. And when we go to adjust these boundaries, we're going to adjust them with the values of 1 and 9 in place of the values of 1 and 3, substituting these boundaries into this function x squared for g at x. So if we set that up, the definite integral from 1 to 3 for x times e to the x squared, well, the x and the dx will become du. E to the x squared will become e to the u. Well, will become 1/2 du, I should say. That x dx becomes 1/2 du. That e to the x squared becomes e to the u. And those boundaries that were in terms of x from 1 to 3 will adjust to be bounds now in terms of u from 1 to the value of 9. Which means we're just going to be evaluating the antiderivative of e to the u, which is just e to the u, across those new boundaries from 1 to 9. So this is going to be 1/2 e to the 9th minus e to the 1st, which is just going to be 1/2 times the quantity e to the 9th minus e. I don't know why I'm using brackets at the end here. Let me throw that into a set of parentheses in the end. All right. And thus, we might point out that this antiderivative seen here in terms of x across these boundaries from 1 to 3 is then going to be equal to this quantity 1/2 times e to the 9th minus e. Right? And that will be our end result here. You'll notice we did not have to return to the antiderivative function for e to the x. Because we adjusted our boundaries to be in terms of u, we only had to evaluate now e to the u, the antiderivative in terms of u, across those boundaries in terms of u, from u equal to 1 to u equal to 9. And it becomes a little bit quicker of a process. This formulation above does get a little muddled here. It can be a little confusing to the end, right? But it is, in process, a rather simplified process. We're adjusting our boundaries here. We can obtain this as our definite integral calculation in terms of u, where you just perform the entire calculation at that point in terms of u, until you get to the final value at the end. All right. Definite integrals are interested in, will produce numerical values, whereas indefinites, antiderivatives, will be families of functions. So here we get this numerical value as our answer. Got one more for you, folks. So here's one. Consider the definite integral from 2 to 3 for the quantity 5x times the quantity x squared plus 1 quantity cubed. Now, what we can do here is we can let u be the function x squared plus 1. Let that be some function of x. That means du dx would be 2x, or 1/2 du would be equal to the x dx. And this value of x and this value of dx would get substituted out with 1/2 du. And the quantity x squared plus 1 would be substituted in with the value of u, and you'd have u cubed as the antiderivative. Now this 5 is just going to be a constant multiple and work it out itself out in front with the 1/2 in value. If we consider adjusting our bounds at x equal to 2, u will equal g at 2, which will equal 5, and at x equal to 3, u will equal g at 3, which will equal 10. So if we go to set up our antiderivative, or our definite integral calculation in this case, that x dx will get replaced with 1/2 du, and that 5, being a constant multiple, will bring itself out in front with the 1/2 as a 5/2, and your du will stay inside the integral as the differentials for the variable u, and the statement x squared plus 1 cubed would turn into the statement u cubed. Now u cubed's antiderivative is 1/4, and then our adjusted boundaries from 2 to 3, substituting in 2 and 3 into this statement for g, produce upper boundary, or new lower and upper boundaries at 5 and 10. Those are our values of x squared plus 1. 2 squared plus 1 is 5. 3 squared plus 1 is 10. So those are our new bounds. U cubed's antiderivative is 1/4 u to the 4th. I can factor out the 1/4 with the 5/2 to make 5/8, and I'm evaluating then u to the 4th across these boundaries from 5 to 10. Let me actually maybe show that step in there. Like this here, this is going to come from 5 raised to the 4th power, and this 10,000 is going to come from 10 raised to the 4th power. That 1/4 is brought out in front as a constant multiple with this value of 5/8. So that gives us 5/8 of 10,000 minus 625, which is 5/8 of 9,375, or 46,875 divided by 8. All right. A little less than what? 6,000 in there. All right. Thus, did I say it here? Thus, this antiderivative seen here is equal to this result seen here. Oop, that is going to be a pain, huh? 46,875 eighths in value. And that is variable substitution. You can perform it here in this definitive case, where you can set up the variable substitution in terms of the variable you're substituting into the composition. And you can leave it in terms of that variable if you adjust your bounds. And it becomes just a definite integral calculation with respect to u. In the case of a definite integral calculation, an indefinite, the case for an antiderivative calculation, when you perform the substitution, you are going to set up your calculation in terms of u, where you're going to perform that antiderivative calculation in terms of u and produce its simplest form, where then you do have to go back in and substitute back in for u your quantity in terms of x. And that's the case for an indefinite integral and how that's handled in variable substitution. Now, both the variable substitution methods develop from this understanding of chain rule, where what you're looking at in your calculation is you are looking for a composite of two functions to begin with, where if you took the interior function's derivative, you would find a multiple of that derivative as another factor, as the other factor incorporated into the integrand of the integration. This would be the result that would be produced from a chain rule for the differentiation for what would be the antiderivative of our function little f in this composition, evaluated at its interior function of little g of x. Right? And this breakdown of chain rule inversed into the integration operation, right, gives us a method for integration known as variable substitution. And it is this advanced method, folks. All right. That is about all the techniques we're going to discuss this semester with respect to calculating antiderivatives and definite integrals, calculating net areas. This is the one advanced technique that we kind of take a peek at this semester. You do want to be familiar with this technique coming back in Calc 2. You're going to be looking at a lot of applications of integrations where you're going to at times be having to apply variable substitution in that process. And then after you spend a chapter on looking at application of integration, we're going to come back to looking at a few more advanced techniques for integration. And by the end of Calc 2, you're going to have a handful of advanced techniques that can also help you find the antiderivatives of functions or calculate the definite integrals, right, in more complex scenarios. All right. But this is the first of several advanced techniques, the rest of which you'll be presented with in Calc 2. But as you go into Calc 2, you're going to want to be familiar with the process known as variable substitution. All right, let me get this set up. Switch over. And I'll say, yeah, folks, this is, I have a couple other videos I might want to put out for you Calc 1 students. I know we probably want to talk about average value of a function. I do have the plans and the notes for that. We probably ought to also maybe talk about what's called initial value problems. And I have the plans and the notes for that. And then we may go back and talk about a couple more things with the application of differentiation. I wasn't able to get there this semester with some of it, and I'll go back and see what I can put together in the way of notes. I'll see if I can get that done. Those last two might be if statements. All right. But with that said, I will probably see you in a couple more videos this semester. Then my plan is, and fingers crossed, because it does sound like it might be a busy semester for me next semester, is I am going to be teaching Calc 2, and I do have videos for Calc 2 already, but I feel like updating them. Rewriting the notes to kind of fall more in line with what I've written here for Calc 1, and then updating the videos to kind of go along with those note sets. That's kind of where I think I'm going to be heading into Calc 2 and Calc 3 over the next year here. So, folks, hopefully you hang out with me and continue your study here. And if not, I wish you the best of luck. And I will see you next time in the next video.